Situation. Just before 6 p.m., students entered the classroom to find Mr. Fees dead of an apparent homicide. Everyone said they saw it coming. At 6, the temperature of the body is 80 degrees, while at 7 p.m. it was 75 degrees. It took a while for the campus police to get through the party. If the room is kept at a constant temperature of 70 degrees Fahrenheit, what is the time of death? So from that paragraph, we learn a few things. We learn that at 6 p.m. the temperature of the body is 80 degrees. At 7 p.m. the temperature of the body is 75 degrees. And the constant temperature of the room is at 70 degrees. So to find the time of death, the first thing we need to find out is the K value, also known as the decay rate. Basically, that means what the rate is of Mr. Fee's body cooling per minute. And this is the formula we're going to use. This formula comes from Newton's law of cooling. T base A is our ambient temperature. T base O is the temperature of an object at a given point. K, we know, is our K value, and lowercase t is time. So again, the ambient temperature of the room is 70 degrees. Temperature of an object at a given point, we're going to use 80 degrees. That was the Mr. Fee's temperature at 6 p.m. And the time that we're looking for is 60, which is minutes. So we're going to plug all those into our equation. So T of t equals 70 plus 80 minus 70 base E of negative K times 60. And since we want to find out per minute, we know from 6 p.m. to 7 p.m. the temperature dropped from 80 degrees to 75 degrees. So we're going to plug 75 in for our T of t right here. Now we're going to start solving. So first thing we do is subtract 70 from both sides. And we can also subtract the numbers in the parentheses together. So 75 minus 70 equals 5, and 5 equals 10 base E of 60K. We will then take 10, divide that by both sides, and that gives us 5 over 10, or 1/2, equals E of negative 60K. So we know that the natural log of E is 1. So what we're going to do is take the natural log of both sides so we get the same base. So that will give us the natural log of 1/2 equals negative 60 times K. And then if we divide negative 60 from both sides, that will give us our K value, or our decay rate, which is negative 0.0115. Now that we have our decay rate, we'll go back to the original equation that we had from Newton's law of cooling, and we'll plug our K value in there, right there, negative 0.0115, along with our ambient temperature, right there, and the temperature of an object at a given point, which is going to be 6 p.m. for us. And we want to know how long it's been since Mr. Fees died. So since the average body temperature is 98.6, we're going to put 98.6 right here. And we're going to start figuring out our equation again. So we take 70 away from both sides, and that gives us 28.6 equals 10 base E to the negative 0.0115 times T. Again, we divide both sides by 10. That gives us 28.6 divided by 10 equals E to the negative 0.0115 times T. Again, the natural log of E is 1, so we're going to take the natural log of both sides to get the same base. That gives us the natural log of 28.6 divided by 10 equals negative 0.0115 times T. And if we take negative 0.0115, divide that by both sides, well, we get a time of 91.38 minutes. So with our K value being negative 0.0115, our time 91.38 minutes, that's from death to discovery. So we can approximate the time of death as 4:29 p.m.